So Laura Escobar from Washington University in St. Louis is going to be continuing the tale of two polytopes with a tale of two polytopes 2, the harmonic polytope.
So first, again, I want to echo what other people have said, and thank you so much for organizing this, and I'm very excited to be one of the speakers, and I'm also excited and thankful to Federico for giving a beautiful talk that motivates part of this work. So as said before, this is joint work with Federico Ardila. So let me start immediately by defining the harmonic polytope. So we have that the permutahedron is the convex hull of the permutations of an element. So here we have the two-dimensional permutahedron, and here we have the three-dimensional permutahedron. And we're gonna, just as in Federico's talk, we are gonna define a polytope that lives in a product of two r to the n's. So we're gonna choose two standard bases for r to the n. And first, we're gonna define a simplex to be the convex hull of the EIs plus FIs. So this is gonna be an n-1 dimensional simplex living in the product of these two r to the n's. And with that, we can define the harmonic polytope to be the Minkowski sum of the product of two permutahedra and plus that simplex. So let's look at an example in case you don't think much about like Minkowski sums. But here on the right, I have the two-dimensional harmonic polytope, and you remember Federico's picture, it agrees with his bipermutahedron, but that is only gonna happen in 2 dimensions. And I label the vertices with honestly what they are. I just wrote them into rows to be very explicit that the top row corresponds to R2 and the bottom row corresponds to R2. So for example, if we take this vertex, we can, this is gonna be the sum of, well, we take something in the product of two permutahedra. So we have 1, 2, 1, 2. This is in the product of the two permutahedron, and you add something in the simplex, which is gonna be, oh, did I screw up? Yeah, I always screw that up. Oh, sorry. No, that's correct. No, it is correct. Okay. So you add 0, 1, 0, 1, and then you get that point. So this is gonna lie inside the harmonic polytope. All of the vertices can be realized in this form. You pick a permutation on the top, a permutation on the bottom, and you add some matrix of this form. And you can see here that this polytope, just as the bipermutahedron, is 2n-2 dimensional. So if you add the top rows, you get the same number as if you add the bottom rows, and that is always a constant. So, well, I want to tie in. So the two talks are somewhat independent, but I do want to start by giving a relationship between the two talks. So the harmonic polytope, Federico mentioned, he basically gave this statement, but he gave it in terms of fans and not in terms of polytopes. So I'll rephrase it in terms of polytopes, that the harmonic polytope is a Minkowski summand of a multiple of the bimutrahedron that Federico told us a little bit about. And that, again, that follows from the fact that if you look at the normal fan of this polytope that we have over here, well, it agrees with the fan that Federico had in the previous talk, but for higher dimensions, the normal fan of the harmonic polytope can be refined to make it be the bipermutahedral fan that Federico defined. So let's start by talking about the combinatorics of this polytope. So we decided to label the faces by something that we are calling harmonic triples on N, and this follows naturally from the fan structure of the harmonic fan. So what is a harmonic triple? It consists of 3 pieces of information. So one is a set K. So we have a non-empty set K. And we are gonna take 2 order partitions of the elements of N. And what we want, so we will see an example in a second, but we want that when you restrict the first partition to the elements in K, and you compare it with the restriction of the second partition to the elements of K, they should be opposite of each other. And the second condition is a little bit more technical, and it says that if you pick something not in your set, and that happens to be in the same or in a later block than something in your set K, in one of the set partitions, then the opposite needs to happen in the other one. So let's relabel the harmonic polytope that we had before. So now I'm labeling it by harmonic triples. So I don't know, let's, for example, take this one. So if we take this harmonic triple, well, the set here is 2, and we see, well, 1 and 2 they're in the same block. 1 and 2 are in the same block. So that tells us that one needs to be before the 2 in the other block. And so if you define the harmonic polytope in that way, or the harmonic triples in that way, here we have all the potential harmonic triples on 2 elements, you will get that you can label the faces of the harmonic polytope in that way. So using that labeling of the faces of the harmonic polytope, we were able to count them. So the number of vertices is going to be equal to n factorial squared times the harmonic series of n. So that's why we decided to call it the harmonic polytope. And we counted the number of facets, and we got that it's 3n minus 3, and this is the same as the number of facets of the bipermutahedron of the previous talk. So, and I want to emphasize one thing that ties with something that Federico told us, but for sure, this polytope is simplicial for the one I drew, but in general, for higher dimensions, it's not going to be simplicial. Like you go to the harmonic polytope 3, 3, and that one's already not going to be simplicial. So I want to spend, so there's other beautiful combinatorial properties of the harmonic polytope that we studied, but to save time, I wanted to choose one of the combinatorial properties that we studied that we liked the most, and that was computing the volume of this polytope. So that's what I'm going to spend the rest of the talk talking about, what it is and how to compute it. So namely, let's just, because I know a lot of people don't often think about polytopes, so I want to make sure that we're all on the same page. So what do I mean by volume? Because I told you, well, I'm computing the volume of a low dimensional polytope, so the volume already would be 0, of course, and that's of course not what I mean. So what I mean is volume in this sense. So we're going to have a d-dimensional polytope on an affine dimensional d plane, which is the case for our harmonic polytope. And what we're going to have is we're going to be measuring the volume of the polytope on that affine plane. So it's the affine plane I told you at the beginning. And very concretely, what I mean by normalizing is that I'm going to take the intersection of this affine plane L with the lattice in R to the n, and I'm going to normalize the volume so that the volume of the smallest parallelotope that has vertices in that intersection has volume 1. So it's a very usual thing to do when you want to compute volumes of polytopes inside affine planes. And to do that, well, if you remember the definition of the harmonic polytope, we define it in terms of a Minkowski sum of 2 polytopes. And thus, it's very useful to, when you want to compute the volume of such polytopes, to use the theory of mixed volumes. So this is like, I'm just writing it in our very concrete case where we are just adding, well, this is a bit more general, but we remember we were adding just 2 polytopes to define the harmonic polytope. So when you want to find the volume of a sum of polytopes, you can just add a bunch of what are called mixed volumes. And I should say that the sum is over all ordered sequences. And yeah, so that's what the strategy that we will follow to compute the mixed volume. Now, let's see what it means in terms of the permutahedron very quickly. So I was gonna do the whole computation, but instead I'll just give you a main idea for what happens in the permutahedron. So we have the permutahedron. This is a classical fact that it's a translation of a Minkowski sum of adding intervals. So here, the delta, I'm gonna denote by delta ij the convex hull of ei and ej, so it's just an interval. And if you add these 3 intervals, you're gonna get this hexagon, which is the permutahedron pi 3. And well, using that, what does that mean in terms of mixed volumes? So in terms of mixed volumes, that tells us that the volume of the permutahedron is gonna be the sum of all these mixed volumes. And over here, if you notice, here, like this has a coefficient of 2 because the mixed volume is symmetric. So I just combine terms. So, yeah. But let's translate it into the context of the harmonic polytope. So as like Okay, so here I'm reminding us what the harmonic polytope is. And therefore, like using this notion, like this expansion of the permutohedron into Minkowski sum of intervals, we can similarly give an expansion of the harmonic polytope into a sum of the simplex that I told you before, the n-1 dimensional simplex, with a bunch of intervals, where I'm denoting by delta ij bar as the convex hull of fi and fj. Like, so these are the segments in the first R, and these are the line segments in the second R. So the conclusion of this slide.
A quick question in the chat. Can we, there's, what are R and S?
Oh, where is, oh, yeah, okay. So I'll say that in a second, and that's a good point because I realized in my setup that I cannot really see the chat. So I apologize for all the questions I might have ignored. Okay, so here we can compute the volume of the harmonic polytope by evaluating various mixed volumes. So I'm gonna denote them by a G and G bar, where this is not very well defined, but I'll tell you in a second. So here R and S are just, they're just, you pick a number in between, like R and S is any number between 0 and 2n-2, because you want to have, it doesn't really matter, like the important thing is that you have the right number of terms here. So if you remember when you have the permutohedron, here we only had 2 terms, and that's because the permutohedron is 2-dimensional. So you just, R and S are just 2, like here, going back to this, they're just 2 numbers such that they're between 0 and 2n-2, so that you have the right number of terms when you're evaluating the mixed volume. Okay, so how do we compute mixed volumes? So in order to compute mixed volumes, well, this is kind of backwards from this theorem, but this is an idea that Poznikov had, and it's that, well, let's use the following theorem. So the following theorem is, in very general terms, going to relate solving systems of equations to computing mixed volumes, and therefore to computing volumes of polytopes. So what does it say? So it says that if you have d finite sets in Z to the D, and you take the convex hull of those d finite sets, and you pick like some sufficiently generic coefficients, and I'll say a little bit more about sufficiently generic, but at this point of the theorem, you should just think you pick coefficients randomly. So then the number of solutions in C star to the D to the following system of equations, where you have it, I mean, this is for those of you that think about Newton polytopes, the Newton polytope of this equation is going to be exactly this polytope, but it's just an expansion where you multiply a coefficient times x to the, yeah, so if you have a point alpha, which is, I want 0. Let's say you have the alpha equals 1,2, that is in A1, then this is gonna contribute to the first polynomial, the monomial x to the alpha, which is gonna be x1 times x2 squared, or x1 to the first power times x2 squared. So you use this rule to construct D polynomials. That gives you a system of equations. You solve it, and since you pick equations to be sufficiently generic, the number of solutions is gonna be finite, and it's gonna be equal to a mixed volume, D factorial times a mixed volume. So in this sense, you can use systems of equations to evaluate mixed volumes if you're able to solve them. So in general, this can be very difficult, but we will see that for our harmonic polytope, we are able to do that. So one corollary that I wanna say is that, well, this one, we're gonna use the theorem above, the BKK theorem, in many settings, but there's a nice specialization where you have that your polytope lies in an affine n-1 dimensional plane. And then you can, instead of, like, again, if you just looked at the volume in R to the n would be 0, but this tells you that, oh, it doesn't matter. If you're in a smaller dimensional plane, you can instead count solutions in here, where this is gonna tell you that you're rescaling the x1 up to the x d that you have, or in other words, you can think of this as setting one of the variables equals to 1. So you write a system of equations, and then afterwards you set one of the variables equal to 1, and then you can apply the Bernstein-Khovansky-Kushnirenko theorem to count the number of solutions to a system of equations, and thus the mixed volume. So very briefly, like, what does that mean? So let's try to compute the mixed volume of delta 1, 2, delta 1, 2. So what is the system of equations associated to this? This is gonna be lambda, so yeah, so remember this was the convex hull of E1, E2, and both of them are that. So this is the system of equations that we get is gonna be lambda 1, 1, x1 plus lambda 1, 2, x2, lambda 2, 1, x1 plus lambda 2, 2, x2. This is gonna be equal to 0, equal to 0. And well, how many solutions does this have? This is gonna have, well, here, again, this polytope lives in an affine plane, so we also wanna set x1 equals 1, and hopefully this is very clear, very concrete that this has no solution. And thus, this tells us then that the mixed volume is gonna be 0. And similarly, you can, like, one can compute the mixed volume of 1, 2, delta 1, 3, and you will, well, if you construct the system of equations for it, you'll see that 2 factorial, well, the system of equations is gonna have one solution, so 2 factorial times that mixed volume is gonna be 1. And using this, you can compute the volume of the permutahedron, looking at the equation from the last slide, which is gonna be 3. And this strategy was exploited by Poznikov to give a very nice proof that the volume of the permutahedron is gonna be equal to the number of trees on n vertices, because he showed that, okay, so in this case, he related when the mixed volume is non-zero and when it's 0 exactly to graphs on n vertices. So he said, oh, the mixed volume is gonna be 0 if you construct a graph that is not a tree, and the mixed volume is gonna be 1 if you can construct a graph that is a tree, and he used that to give a very beautiful proof for the computation of the volume of the permutahedron. But now we're gonna apply this to constructing or evaluating the volume of the harmonic polytope. So in our case, we have that our harmonic polytope lies in an n-2 dimensional plane. So we're gonna instead count number of solutions in this quotient of torus. And again, this is like rescaling the first n entries. This is rescaling the last n entries. So we can think of this as setting one of the variables equal to 1 and the other variable equal to 1. So this is like how you should think, that we're counting solutions. We're gonna have a system of equations, and we're always gonna set one of the variables equal to 1, and one of the first n variables equal to 1, and one of the last variables equal to 1. So I'll do one example very concretely so that you can understand all the objects that come into our formula for evaluating the volume of the harmonic polytope. So for that, and there's gonna be a lot of graphs. So we're gonna first, inspired in what Poznikov did, we're gonna encode a sequence. So remember, we were looking at volume, our mixed volumes, I rewrote it over here. Our mixed volumes were of this form, so we had a sequence of R element or R pairs, and we had a sequence of S pairs, and we're gonna encode them in a graph, right? So like when here, this is gonna correspond to this like delta 1, 2, delta 3, 4, delta 5, 6. So each pair is gonna give us an edge of the graph. And here I introduced this notation before, but I hadn't explained it. Now that I'm encoding the sequence into graphs G and G bar, I'm gonna denote the mixed volume that we wanna compute into the mixed volume of G and G bar. And the whole point is we wanna use Bernstein-Khovansky-Kushnirenko theorem to compute the mixed volume. So let me tell you what the system of equations we get. So abstractly is just this, but it's very straightforward. So whenever we have an edge, so for example, we have the edge 1, 2. So the edge 1, 2 tells us or gives us the equation x1 is equal to lambda 2 or lambda 1, 2, x2, for example. So each of the edges gives us an equation like this for the graph G. Similarly, each of the edges of the graph G bar gives us a linear equation. And lastly, we're gonna have K equations that are coming from this simplex. Okay, so these equations are of degree 2. Okay. So let's continue our example. So what we're gonna do next is we're gonna transform, so we wanna find the number of solutions. So because Bernstein-Khovansky equation-Urenco theorem tells us that 10 factorial times this mixed volume is the number of solutions to that system of equations that I wrote there. And what we did, how we evaluated this mixed volume is we translated this into computing the volume of a well-known polytope. That is going to be, it's a polytope constructed from a bipartite graph. So how did we relate that? Well, we did a little trick that is not too fancy, but it's pleasant. And it's that for each of the connected components of G, so for example, this is like we have 3 connected components, we introduce 3 variables. And for each of the connected components of G bar, we introduce a variable.
I'm standing up for 3 minutes left.
Ah, okay. So now, and we introduce linear equations, like relating each of those like new variables to one of the variables in each connected component. So then what we did is we eliminated the variables, the original variables, x1 up to xn, and we obtained this system of equations for some coefficients which will happen to be sufficiently generic, and thus we will be able to use BKK to compute the volume of those polytopes. And yeah, because of time, I won't go into too much detail, but these aren't hard to find. Like you can use the path structure of each of the graphs to actually give very explicit formulas for each of these coefficients. So BKK tells us that the number of solutions to this system of equations is equal to the volume of this polytope. So I'm just labeling the e's. So this is just an element of R2. So yeah, these are bases like E12, E24, and E56 are basis elements of R to the 3, and I'm labeling based on the connected components. And similarly for the F's. And BKK, like similarly, the Newton polytopes of these equations are these polytopes. So BKK tells us computing the volume is gonna tell us the number of solutions to that system of equations. And this is a known polytope. So Poznikov studied it in his work on generalized permutohedron. It's called the edge polytope of a bipartite graph. So this is a bipartite graph where the vertices are the connected components of G and G bar, and you connect 2 connected components if they share, like, so because both of them have a 1, you connect them. So this is like, you can think of this as partitions now once you think of the connected components, and you connect 2 vertices if they share a part. So how does, and Poznikov told us how to compute the volume of these polytopes. So how do we do it? So this is a bit technical. So, but I guess the takeout from this slide is just that you can compute the volume of edge polytopes by counting integer points in some other very concrete polytope. So given a bipartite graph, you can construct a simplex that has, it's gonna be the convex hull of as many vertices as the vertices in V. And for each of the vertices in U, you can define some other simplex that is kind of encoding the adjacency or the neighbors of that vertex U to the other vertices. And using that, you can construct this polytope, which is going to be a Minkowski difference. And if you count the number of integer points in that polytope, that tells you what the volume of the edge polytope is. So in our example, we have this graph, and the edge polytope is just gonna be just the sum of this is gonna this part is a what a segment, a line segment, and this is a point. So it's a translation of a line segment that only has 2 lattice points. So that tells us that the number of solutions to this system of equations is equal to the volume 3 factorial times the volume of our edge polytope, which is 2. So again, we translated finding the number of solutions to system of equations into counting the number of integer points. And one thing that maybe I forgot to say before is that the number of solutions to the system of equations associated to the edge polytope is the same as the number of solutions to the system of equations that was giving us the mixed volume that we wanted to find. So using all this, we were able to compute the volume of the harmonic polytope. So first, there's this disclaimer that if the graphs,
Time's up here, so I don't want to interrupt, but is it just one more slide here?
Yeah, this is just the last slide. Yeah.
Okay.
So if you have 2 acyclic graphs, then you will have that the mixed volume is going to be 0. I'll just show it all. Yeah, why not? So, and when G and D bar are acyclic graphs and you construct a bipartite graph using the connected components just as we did before, you can relate the mixed volume to the volume of the edge polytope to the number of lattice points in this polytope. And using this, we computed just the volume of the harmonic polytope. So this is the volume of the harmonic polytope. Is you take the sum over all connected bipartite multigraphs, and you take the number of lattice points in this polytope P gamma minus. You need to divide this just like if you follow what you need to divide by. This is the coefficient that you will be dividing by, where this is the number of vertices. And here, this is going to encode the fact that you want acyclic graphs on, like you can imagine putting pairs of acyclic graphs on each of the vertices of the bipartite multigraph. But yeah, so I'll finish there. Just you can stare at the table of some of the some of the volumes we were able to compute by hand.
Okay, thank you very much, Laura. Give her a round of applause. All right. Are there questions? So there are some questions from during the middle of the talk. There was one that said, which one has largest volume and opposite in one sense? I think those are questions from earlier, so maybe those people can clarify in the chat. But a more recent question just at the end here. So the volume is not an integer from Tuotros. And which one has larger volume, the harmonic polytope or the associated bipyrimidahedron?
Oh, that's a good question, because so there is no formula for no known formula for the volume of the bipyrimidahedron from the previous talk, because it can be hard to do. Yeah, I guess we haven't figured out how to do that one. So, but when we were doing tables, I forget, we did do tables, and for small numbers, I forget which one had the bigger one. Do you remember, Federico?
I was looking through the computations that you did. So the bipyrimidahedron is a lot bigger.
Thank you.
Great. Well, I think in the interest of time, let's thank Laura again. And another round of applause. So thank you very much. And we're going to move to the first break.